You know, you might think the operating system on your phone is the absolute peak of technology, right? But what if I told you the OS running a simple traffic light could be way more complex? It's because not all operating systems are created equal. They're actually highly specialized tools, each one built to solve a very specific problem. So let's dive into how we got from these giant room-sized computers to the tiny powerhouses we all have in our pockets. So let's just start with this question. Why on earth would a life support machine, where even a millisecond of delay could be totally catastrophic, need a different kind of brain than your smartphone, which just needs to let you scroll through social media while your music is playing? Well, the answer to that is really the core of our story today. Different jobs demand different, and I mean highly specialized, operating systems. Okay, our journey starts way back in the day when computers were absolute giants that filled entire rooms. And these mainframes had a simple but massive problem to solve. How do you chew through mountains of repetitive work without a single hiccup? The answer was the first real type of operating system. And here it is, the batch operating system, one of the earliest forms of OS you can see on this timeline. Its genius was just in its sheer brute force simplicity. See, instead of a human operator feeding it one job at a time, the system would group similar jobs, like say all the company payroll calculations, into a single batch. Then it would just process them one after another with zero human interaction needed. Super efficient. Now, this is where it gets really interesting, because there was a crucial trade-off. The advantage? Unbelievable efficiency for those huge repetitive tasks, for sure. But the disadvantage? Well, that basically shaped everything that came next. Imagine this. You'd hand over a stack of punch cards, that's your program, to an operator, and then you just leave. You'd come back hours, maybe even days later to see if your program even worked. That was a reality. No interaction, just a whole lot of waiting.
Right, so while the batch OS was efficient, it wasn't interactive. Not at all. The next great leap in operating systems was all about solving that exact problem. How do you let lots of people use one powerful, super expensive computer all at the same time? And the solution was just brilliantly elegant, the time-sharing OS. You can kind of see how it works here. The operating system acts like this incredibly fast manager, slicing up the CPU's attention into tiny fractions of a second. It gives each user a tiny little time slot, then boom, it switches to the next one, then the next. And this happens so fast that it creates the illusion that everyone is using the computer at the exact same time. This was a total revolution, paving the way for systems like Unix. Now, this brings up two ideas that people often mix up but are really important to get: multiprogramming and multitasking. Let's break it down. Multiprogramming is all about keeping the CPU as busy as possible. So when one program is waiting for something, the OS cleverly switches the CPU over to another program that's ready to go. But multitasking, well, that's what you experience. It's the magic that lets you run multiple apps at once. You know, listening to music while you're typing in a document. Modern systems like Windows and Mac OS, they are absolute masters of this. Okay, so we've made computers interactive, and we've made them personal. What's the next huge problem to solve? Distance. How do we get all these individual computers to start talking to each other and sharing things over a network?
And this is where two main paths kind of emerged. On one side, you've got the network OS, like Windows Server. In this setup, each computer's independent, it has its own OS, but they're all aware of each other. They can share files and printers pretty easily. But on the other side, a distributed OS takes it a huge step further. It weaves a bunch of computers together so tightly that they actually look and act like a single, massively powerful system. When you think about the colossal systems that power Google, yep, that's distributed computing on an epic scale. All right, let's jump to the modern era and see how this all comes together. Because now we have operating systems that are hyper-specialized for very specific, really demanding jobs. These aren't your general-purpose desktop systems. These are the elite specialists. So meet the real-time operating system, or RTOS for short. For an RTOS, just getting the right answer isn't good enough. It has to get the right answer within a strict, unmissable deadline. We're talking about the systems that run air traffic control, those life support machines we mentioned, and industrial robots. In these jobs, timing isn't just important, it's pretty much the only thing that matters. And even within this specialty, there are two different flavors. First up, you have hard real-time systems. This is where missing a deadline means absolute catastrophic failure. Think about a car's airbag system. It has to go off at the right millisecond every single time. No excuses. Then there's soft real-time, where deadlines are still important, but, missing one occasionally isn't the end of the world. Think about streaming video. A few dropped frames or a bit of buffering is annoying, but it's acceptable. And finally, let's talk about the specialist OS you're probably holding in your hand right now, the mobile OS. Your phone's operating system, whether it's Android or iOS, is a true marvel of specialization. It is constantly juggling this unique set of problems, managing constant touch input, being super aggressive about conserving battery life, coordinating a dozen different sensors from GPS to gyroscopes, and running a secure ecosystem of apps. It's a really incredible balancing act. So as we've seen, the history of operating systems isn't just a list of technologies. It's really a story of constant evolution, of brilliant engineers seeing a new problem and crafting a specific, elegant solution to solve it. So let's just quickly retrace our steps. We started with the raw, brute force efficiency of the batch OS. Then, we made computers personal and interactive with time sharing. After that, we connected them across huge distances with network and distributed systems. And finally, we specialized them for the most critical and personal tasks with real-time and mobile operating systems. Each step was a new solution for a new challenge. And that brings us to one final big thought. We are now entering a world that's going to be dominated by artificial intelligence and the Internet of Things, where literally billions of tiny smart devices are always connected. So what new unforeseen problems is that going to create? And what will the next great evolution of the operating system have to look like to solve them?